we will now learn about a theorem that tells us how to compute the homology of a tensor product of chain complexes. And this theorem will later be applied to the situation of a product of spaces, and we will get a formula how to compute the homology, the singular homology, of a product of two topological spaces. So let me first introduce the tensor product of two chain complexes. And in this video, we will assume, mostly for convenience, that our ring is a commutative ring. So we don't have to distinguish between left and right modules. So let's consider C star and D star, two chain complexes of R modules. Then we declare the tensor product of those. As an R chain complex that has the following chain modules, so in degree n. This is the direct sum over P plus Q equals n of all the modules C P tensor dq. And the differentials in this tensor product are declared as follows. So I will give you the differential on the elementary tensors. So this is my generic symbol for the differential, both in C star as well as in D star. And the differential applied to an elementary tensor is then, well, it looks like a product formula in calculus, where you take first the differential in x, tensor y, plus then up to sine x tensor the differential of y. And the differential, the degree that you see here, is just the chain group in which this x lives. So if x is an element in Cp, then the degree of x is p. And you can easily check, and you should probably check, that this is a differential. So if you apply it twice to an elementary tensor or to an arbitrary element, then it gives you 0. And in that calculation, you see that it's really important to have this sign here. So if you do this without the sign, you won't get that this is a differential, so that dd is equal to 0. So I want to discuss a theorem called Künneth theorem that gives you, at least if the ground ring is a principal ideal domain, an easy way to compute the homology of a tensor product from the homologies of the individual chain complexes. So let R be principal ideal domain. And let C star and D star be what's often called positive R chain complexes, meaning that there are no non-zero chain modules in negative degrees. And furthermore, the chain modules of C star should be projective as an R module. Well, in that situation, there is a short exact sequence where you have first the tensor products of the homologies. Then in the middle you have what you want to compute, the homology of the tensor product of the chain complexes. And then in general you have a correction term given by the following Tor 1 term. Remember, there is no higher Tor if you have a principal ideal domain. This here is the Tor term, the homology. C star and D star in, oh, I'm missing something. Sorry for that. Let me move that a little bit to the right. Because this is not just one Tor term, this is actually a sum. But now over all ij that sum up to n minus 1. And here we have hj d star. So we have this sequence, and similarly as before, this sequence also splits, but in a not necessarily natural way.
So this time this means neither in C nor in D, the splitting is natural.
Right, right. So this theorem looks very similar to the theorem that you discussed before, the universal coefficient theorem. And indeed, if one of these chain complexes just consists, say, of one module in degree 0, then indeed it is just the previous theorem. So assume that D star consists just of D0, so there are no differentials, nothing. In particular, there is no homology beyond H0, and H0 D star is just D0, then this is exactly the previous theorem. So if you want, this is a generalization where the coefficient themselves are chain complexes. But the importance of that is not, if you phrase it like that, it sounds like an arbitrary generalization, but the importance of that stems from the fact that we will apply it to singular chain complexes of two spaces, and we will then see that the middle term really computes the homology of the product, the single homology of the product of those two spaces. But the proof reminds a bit of the previous proof. It's similar in some respects. And let's jump into the proof now. I will prove it. I will not talk about the split, but I will prove that we have this short exact sequence. And we will first consider the case where the chain complex C star, so the projective chain complex in the assumption, has zero differentials. This has some consequences. Well, one consequence is that the homology of C star is just C star itself. The other consequence is for the tensor product of C star and D star, because for the differential of this tensor product, we then have that remember, this was the sum of two terms, but the differential of C now vanishes, and what's left over is up to sine just C tensor differential applied to D. And this means that the tensor product of these chain complexes is really up to sign a direct sum of chain complexes where you have a fixed module Ci tensored over R with the chain complex D star or a shifted copy of that chain complex. Right? So remember that this chain complex, there's an R here, is the sum in degree n over I plus j equals n. But since the differential is just identity tensor to the differential on D, we can regard this as a direct sum of chain complexes where, again, you just have a fixed module on the left and then tensor a shifted copy of D star, which simplifies the situation a lot. So let's draw some conclusions from that. So if we want to compute the homology now of what we want to compute in this situation, well, the homology of a direct sum of chain complexes is the direct sum of the homology groups. So this is the direct sum, well, maybe two steps. Let me first write Hn of the direct sum of these chain complexes. Direct sum we can just draw out of the homology, and then we have a shifted copy of D star tensored with a module Ci. But now we use the assumption that Ci is a projective module. So tensoring with a projective module is exact. Therefore, whether you tensor before taking homology or tensor after the homology doesn't make a difference. If you want, you can also apply the universal coefficient theorem in that situation and just argue that the Tor term vanished, but it's actually easier than that because it's a projective module. So this is the same as Ci tensor over R of the homology of this shifted D star copy, but of course then this is just Ci tensor R Hn minus I of D star. And now if you want, you could also replace this Ci as Hi of C star. C star has no differentials, so the homology coincides with the chain complex. And then it really looks like what we want to prove. Namely, the homology of the tensor chain complex is given by the sum over the tensor products of the homology. If you look at the statement, this was the statement, except that we had on the right a Tor term, but that Tor term vanishes because here you just have C star and these are projective modules. So it's exactly what we want to prove in the case where C star has vanishing differentials. And now the proof tries to argue from that and to reduce the general situation to this situation. And the trick to do this reduction is similar to what we've seen before. We split the chain complex C star in a short exact sequence where we have the cycles and the boundaries. Each of them we consider as chain complexes with vanishing differentials. So now let C star be arbitrary, I mean an arbitrary projective chain complex. and consider this kind of decomposition of C star, if you want, into a short exact sequence, where we have here the cycles, and here the boundaries. And we consider both of them, as Holger did in the previous video, as chain complexes with zero differentials. And I think you argued that this is then, these are maps, the inclusions are maps of chain complexes. We can also say that the fact that C star is a projective chain complex, that it consists of projective modules, is inherited passes over to these two chain complexes that we see here. And this is location and proof where we use that we have a principal ideal domain. So I add this here. This is still projective because we're talking here about submodules of projective modules.
And maybe it helps to keep in mind that for principal ideal domains, projective modules is the same thing as free modules. So that's just a statement that the submodule of a free module is free again if the ring is a principal ideal domain.
That's a good point. Now we have this arbitrary chain complex, and we have now description of this arbitrary chain complex by a short exact sequence with two chain complexes which satisfy what we assumed before. So for that chain complex and for that chain complex we already have proven the statement, and this should help us now in proving the statement for C star. So what we do first is we tensor this short exact sequence of chain complexes with D star. And I claim that we still get something exact. Let me first write it down. So we tensor with D star, and we still get a short exact sequence of chain complexes. This is due to the fact that these modules are projective, even free. So this sequence here is actually a split exact sequence, and this split exactness here transfers in each degree, because short exact sequence of chain complexes means short exact in each degree. So in each degree it's still exact because you have these splits. And the short exact sequence of chain complexes gives rise to a long exact sequence in homology. Let's write at least part of this long exact sequence. And it's also important to look a bit closer at the boundary homomorphism of that long exact sequence. So I'm claiming that the boundary homomorphism in the associated long exact sequence is induced by the inclusion of, now I have to think, in to this. Also, the boundaries lie in the cycles, and if you look at Hn of this, then the boundary homomorphism goes to Hn minus 1 of that complex. And you see, because of this shift, it makes sense to say that this is induced by this inclusion, tensor the identity on D star. And you really have to look now at the construction of the how did we find this boundary homomorphism, and then you can figure out that this is really indeed induced by the inclusion. It's something that I won't do now. So let's write part of this long exact sequence. Maybe let's give this a name. So I star minus 1, and then it continues here to hn minus 1 c star tensor d star, and so on. And here we have in star. This is the long exact sequence. We can say a bit more about what these homologies are. So remember that these two chain complexes, the chain complex of the cycles and the chain complex of the boundaries, have vanishing differentials. Therefore, this tensor product is really a direct sum of shifted copies of D star, tensored sum module from B star, as we've seen before. Similarly here, so we can say exactly what this is. This is, maybe I may do it in blue to distinguish it from the long exact sequence. This is isomorphic to P plus Q equals N, BP minus 1, HQ D star by the same argument as above. And also here we can say this is the sum. P plus Q equals N CP tensor HQ of D star. All right. We proceed now also in a similar fashion as before. We have this long exact sequence. We want a description of the term that you see here as a short exact sequence of something else. So we break this long exact sequence up into short exact sequences by looking at kernels and co-kernels. And then we obtain a short exact sequence that starts with the co-kernel of in star. Yeah, and then here we replace this here by the kernel of in minus 1 star. So this is exact. So now we only have to figure out what the co-kernel and the kernel are, and hopefully they are what we expect them or what is stated in the theorem. Let's start with the left-hand side, with the co-kernel, and claiming that this is isomorphic to what we want. What's the reason for that? By right exactness of the functor tensoring with HQ star. Okay, so let's have a closer look at this statement. We're building the co-kernel of in star. So let's look at the modules of the map IN star, the target is what you see here. So this direct sum of these tensor products of cycles and HQD star. The domain of the map IN star, well, this is the boundary homomorphism. So the domain is a direct sum of boundaries tensor homology of D star, HQ of D star. And the map IN star is induced by this inclusion. So what you really have for this map IN star is you have the inclusion of boundaries into the cycles tensored with the corresponding homology group of D star and then a direct sum over those. And you build the co-kernel of that map. But the tensor product is right exact. So it doesn't matter whether you first take the co-kernel and then tensor, or you first tensor and build the co-kernel. Therefore, we could also first take the co-kernel of the map induced by the inclusion of the boundaries into the cycles, and then take the tensor product with the homology of D star. But this is exactly what you see here. It's the homology of C star, tensor HQ D star. So that's the identification of the left-hand side. Now, let's identify the kernel of IN minus star. So the ISO IN minus star to the Tor term that's in the statement let me formulate it like that. It results from summing up what we obtain from the universal coefficient theorem. Let me put that in quotation mark. So how do we apply the universal coefficient theorem? I claim we have a short exact sequence. Like that. Let me just see. Actually, no. I want to take this back with UCT. It's actually more elementary what we apply. Let me just say from summing up the following, and then let me write it and then think about it. But it's actually more elementary. So here we have the boundaries, tensor HQ D star, and the inclusion of the boundaries into the cycles. All right, so let's look at this. What we have here is a short exact sequence that we start with, namely the inclusions of the boundaries into the cycles, and then there would be another term, the homology of C star. Okay, so that's a term I just dropped here. But that's a short exact sequence you start with. Then you tensor that short exact sequence with HQ D star. As we know, it won't stay exact. It will stay exact on the right-hand side, but it will not stay exact on the left-hand side, but the correction term on the left-hand side by the long exact sequence for the Tor terms is this Tor term. Now, the long exact sequence goes on. There's actually here, there's where I wrote 0, there is a priori another Tor term, but this other Tor term would be the Tor term of cycles in HQD star, but the cycles are projective, even free modules, so that Tor term vanishes. So what you see here is just a certain fraction of the long exact Tor sequence. And here, what you see here is the kernel of IN minus star. Yes. So what we sum up is not universal coefficient theorem, as I was mistaken to say. What we sum up are these fractions of the long exact sequences of the Tor term. And okay, so I also see the notation is misleading because the kernel of IN minus 1 star is actually the sum over all those. I should not write it like that. Nevertheless, you see that if you sum up all those kernels, then you get the sum over the Tor terms equal to the sum over these kernels, and this is exactly kernel of IN minus star. And that concludes then, if you plug this in here, concludes the proof of the Künneth theorem for tensor products. So let's draw now the topological conclusion from this abstract homological algebra theorem as promised. And for that we need a black box that we will show in the next video, or in a later video, the Eilenberg-Zilber theorem. The Eilenberg-Zilber theorem relates the singular chain complex of a product of spaces to the tensor product of the singular chain complexes. And since we won't prove it now, I will just state it. I already have written it down. It says that there is a natural chain map from the singular chain complex of the product to the tensor product of the singular chain complexes of the individual spaces. And this chain map is a natural chain map, natural in X and in Y. And also, if you impose the condition that it maps a singular zero simplex on the left-hand side, which is just given by a point in X times Y. A zero simplex, singular zero simplex is given by the point it maps to. So it's given by little x, little y in the product. And if you impose that this singular zero simplex is mapped to X tensor Y, to this elementary tensor in Z0X tensor Z0Y, then this chain map is also unique up to natural chain homotopy. There is a reverse statement. If you start from the tensor product of these chain complexes, there is also a natural chain map, and this natural chain map is also unique up to natural chain homotopy. If you impose that this elementary tensor X tensor Y, where again little x, little y stand for points in X and Y and therefore for singular zero simplices, if you impose that they are mapped to X, Y, then there's only one such map up to natural chain homotopy. And that is the Eilenberg-Zilber theorem that will be the result of a very abstract argument. It is good to know it's something that we won't discuss further now, but I should mention that if you take the cellular chain complex and you have CW complexes X and Y, then the product X times Y has a natural CW structure such that the cellular chain complex of the product is even isomorphic to the tensor product of the cellular chain complexes. So knowing the CW structure on a product of CW complexes really gives you kind of trivial Eilenberg-Zilber theorem. You even have an isomorphism. But for singular chain complexes, you want this theorem, you need this theorem that only gives you, by an abstract machinery, this natural chain maps. the fact that they are given by an abstract machinery does not mean that you cannot write down such a map. You can indeed write down this map above here, and I will do it. So let me give you a concrete formula for that. Concrete representative. And this is the Alexander-Whitney map. AW star, let's call it, from singular chain complex of the product to the tensor product. Yeah, what does it do if you apply it to singular simplex, n simplex in x times y? What is a singular simplex in x times y? Well, it's given by two singular simplices, one in x and one in y. So you can write it as sigma comma tau, such a singular simplex. And what you do is you map it to a sum of elementary tensors. What was our notation now for the standard band? Was it E1? Not sure anymore.
For what?
For this restriction of sigma when you define the differentials.
E or V.
E or V.
Yeah.
Good enough. So we had this notation of restricting. Notice that sigma and tau are n, singular n simplices. And now what you have here is an I simplex, tensor, and n minus I simplex. And what's also important about the formula is that ei plus 1 gets repeated here. So that's not a typo. It's not ei plus 2, it's really ei plus 1.
Actually, I think we started counting at 0 all the time, right? So
we did?
It should be E0 until EI and then EI until EN, right?
Okay.
But I mean...
That I can easily change.
Yeah.
What still stays true is that this is repeated, this entry here. And one can compute, well, it is obviously natural in x and y, that's clear, I would say. And it also satisfies this assumption on the zero simplices. And if you believe in the theorem above, this is representative of this unique chain homotopy class then. And you have to, of course, also check that this is indeed a chain map, something that we won't do.
The sum indices are right now, no? The I starts at 0 and runs until n. That's correct, right?
Yeah.
Yeah, okay, never mind, because we changed it on the right-hand side, that's why I wanted to make sure.
Yeah, it was n plus 1 before. Yeah, I think it's correct now. So let me write is a map as in 1. In first statement in the Eilenberg-Zilber theorem. And again, this is called the Alexander-Whitney map. The convention is that every chain map as in 2 is called an Eilenberg-Zilber-map. So there is no such distinguished representative there. And these Eilenberg-Zilber maps are generically denoted by EZ. Is called Eilenberg-Zilber map and denoted generically. Now this machinery that gives you this Eilenberg-Zilber theorem gives you a whole bunch of similar sounding statements. So for example, what you get out of this machinery is also that if you have a self-map of x times y, that is the identity on zero simplices and is natural in x and y, then this is up to natural chain homotopy, also homotopic to the identity. That's another statement you get out of this machinery. Therefore, if you use this extra knowledge, which is not contained in the statement here, you see then that if you compose these two maps, you get a self-map of this. That is the identity on the zero simplices, and therefore it's naturally chain homotopic to the identity, and also in the other direction, vice versa. So the Alexander-Whitney map, or any map as in one, is a chain homotopy inverse, a natural chain homotopy inverse of any Eilenberg-Zilber map. So let's call this a consequence, although it uses some extra knowledge. So these give us natural chain homotopy equivalences. Between the singular chain complex of a product and the tensor product of the singular chain complexes. And now we can apply whatever we know already from the homological algebra about tensor products of chain complexes and their homology to the product of two spaces. And combining this statement here with the abstract Künneth theorem gives us the following statement. So in combination with the Künneth theorem, we now obtain what I want to call the Künneth theorem for homology of spaces. Or products. Okay, there is something to write here. So R has to be principal ideal domain. And then I claim for two spaces, x and y, there is a natural short exact sequence which splits, not in a natural way, but it does split. And it is of the following form. Here we have the tensor product of the homologies. Here we have the homology of the product. And here we have the Tor terms. So the only thing we did here was to replace the middle term, which was in the algebraic Künneth theorem, the homology of the tensor product, by the homology of a chain homotopy equivalent chain complex, namely the singular chain complex of x times y from this Eilenberg-Zilber machinery. And then we get this theorem, and there are some variations of that theorem. So there are, for example, versions of that theorem where you have a relative homology x, a, y, b. Usually need to assume something additional here about these pairs. For example, if x, a and y, b are CW pairs, then you would still have a corresponding Künneth theorem. But in the absolute case, we can deduce it now from what we have so far, or from this black box that we introduced. These Tor terms, in general, of course, do not vanish. There is a situation which I want to state explicitly where this becomes an even cleaner statement, and this is the situation where we have a field. So our ring R is now a field, and we call it K. And then we get the best possible statement, namely the homology of x times y over K is just the sum of tensor products of homologies. And this is due to the fact that over a field, every module is just a vector space, has a basis, so it's a free module, and therefore the Tor term has as entries free modules and henceforth vanishes.
And it's good to remember that Z-mod 2 is a field.
Yeah.
For the purpose of calculations with projective spaces and so forth.